Hello, everyone. I am Kory Prince. I'm a staff engineer on the client engineering team at Airbnb. Today, I'm going to tell my story of building a scalable open source pipeline for device insights at scale using osquery. So most of you in this room have probably heard of osquery. Maybe some of you are using it. If you're not aware, it's a SQL database for device information. So instead of querying an actual database, when you run a query, like select name from apps, it's dynamically pulling all the apps from your system and returning the names of them. It also supports custom extensions. So you can add any custom value you want. If you can pull it programmatically, then you can query it with osquery. And osquery becomes really powerful when you start configuring scheduled queries and start shipping that data somewhere. So that sounds pretty cool, right? Like being able to programmatically and schedule all this device information, but what do we actually use it for? I manage a device fleet and I have a lot of questions, right? Like, what is the version of something? Is Santa patched so, a user can't run the tool that they showed and just disable it? Configuration and state, what's the status of the last monkey run? Was it successful? Performance, is my XEDR using all my battery life? Is it causing our build tools to be too slow? Maybe I'm investigating an incident and I need to see when Puppet started returning errors across the fleet. So I want to be able to go back in time and see what the state of our fleet was at any point in time. But also in real time, right? Like, a patch enforcement's about to go out, and I want to know exactly how many devices have it right this minute, so I'll know how many are about to get blocked. And I think the biggest thing is I need to know the answer to a question that I don't know yet, right? Like, I don't know what's coming tomorrow. Maybe somebody is going to release a vulnerable version of an NPM package because the author let OpenClaw, commit their publishing keys. And I need to find out, who in my org has installed it. So already having that data flowing in where I can quickly react is very powerful. But if all of our devices are generating all this data, we need to send it somewhere useful. At Airbnb, we're a remote company. I can't SSH into someone's device and run osquery. So we need to ship this all somewhere. And a really good option today is a data lakehouse. So what's a data lakehouse? Now I'm going to preface this. I'm not a data engineer. Are there any data engineers here today? Great. Then you won't know if I'm wrong. All right. So really quickly, the concept of a data warehouse has been around for decades. Like when I was in college, we learned about it. It's basically like a giant online database where you send all your data to. It's usually like nightly or weekly data exports. It's like super strong schema. There's lots of reconciliation things. And it's like an expensive database like Oracle, or SQL Server or something. In more recent times, the concept of a data lake took form where you basically just dump all the data into object storage, S3 or something similar, and you query it there, which is much more flexible and it's very cheap, but it lacked many of the features of a data warehouse like governance. But in the last decade, the the data lakehouse has emerged as a hybrid of the best of both worlds, where you get the cheap and fast storage. You can scale out the querying and make it very fast, even on large data sets. But you get the features of traditional databases like transactions and governance. One of the main data formats for a data lakehouse today that's emerged in just the last few years is Apache Icehouse. Apache Iceberg. Iceberg is made up of several layers of files stored in object storage like S3. At the very bottom, there's the data format, which is Parquet. It's basically, think of like a CSV, but instead of it being row-oriented, it's column-oriented because that makes it much more efficient to query. Above that, you have manifest files, which is like a subset of table data. Top of that, you have a manifest list, which is, think of it as a snapshot of this subset of data. And at the very top, you've got the metadata file, which you can think of as like a snapshot of the entire table at any point in time. And then separately, you've got this catalog. that anybody who wants to query this data will first look at the catalog, and the catalog will tell you, here's the snapshot you should be checking. So with all of that fun technical details out of the way, let's look at how to build a data lakehouse. So this is like the basic pipeline that I built for this demo. Up in the top left, you can see osquery. It's shipping all those scheduled queries into Kafka. Kafka is an open source real-time streaming service that can be scaled to handle like millions of events per second. And those are shipped over to Flink, which is a stream processing service and job library. Now, Flink is it's both a service and then you like build a custom job, but it comes with a lot of connectors. So most of your code is like, I want to pull from Kafka and I want to put it in Iceberg. And it actually supports dynamic schema updates. So I don't have to know the format of the osquery events coming in. It will just automatically, like if a new field is added, it'll just update the table to match. In between, I wrote a parsing layer that turns the JSON events from Kafka into structured data. So you get just a JSON blob coming in and then the structured data that Iceberg knows how to write. Flink by far is the most compute intensive part of this pipeline because it's having to deal with reading every single record and transforming it. But it can be scaled to run multiple instances of each task in parallel. In my testing, I'm just running like a single EC2 instance and can do like 100,000 or 120,000 records per second. It also has support for custom metrics. So like my test job has a metric just to see like how many records per osquery table are being processed. But you can think, you know, maybe you have monkey logs coming in and you want a real-time view of like, what's the distribution of monkey runs that are successful versus an error, and you can export that as a metric. So in this diagram, you can see how everything starts to fit together. All the tables and schemas and data are written to Garage, which is basically just S3. It's just an open source alternative like a MinIO. And then once all that data is written, a snapshot is sent to Polaris, which is the Iceberg catalog server. So if we look back at the Iceberg, which you can start to see why it's an iceberg because it sort of stacks, right? Flink is writing all the S3 stuff, that full snapshot of data. And then once it's there, it can tell Polaris, hey, there's a new snapshot, update your catalog to point to the right one. So it can be, that's how it maintains atomic changes, is it's handled through the catalog server, which that's the one thing that's not in S3. It's more of like a traditional database that tracks. And coming back to our overview, the last thing is Trino. Trino is a horizontally scalable SQL engine that supports reading and writing Iceberg data. And it can also be scaled to read millions of rows from thousands of files very quickly. It scales out horizontally, and each one can download what it needs, and then it sort of combines all the data. Now that we've got all the data in Iceberg tables and we have Trino to query it, things can start to get interesting. So in the demo I'm going to show today, we have a couple ways to query a data warehouse. We've got Superset, which is like a web-based data exploration and dashboarding tool that was originally built at Airbnb, and now it's an Apache project. And then I built an MCP server that provides tools both to query Trino, but also it has an environment, like an isolated Python environment where it can run just like a normal agent where it can build Python files to generate charts. And then this MCP server is hooked up to a chat UI I built on top of Chainlit, and you can hook into whatever your favorite LLM is. So before I get to the demo, I do want to take a step back and say, I think it's important in today's age of like put AI in everything to really ask the question, does AI belong here, right? But in this case, AI has a compelling case because it's faster and better at me than writing SQL and building charts. And if you provide the tools in the right way where it doesn't have to read all the data into its context and then spit it back out where it can hallucinate and miss data, but you have it where it's querying it into a file and then writing Python to parse it and generate a chart directly. So the data is not passing through the LLM, it's just looking at the structure. And AI allows people who can't write SQL to query the data. It allows them to see dashboards and charts. And if you provide the right context and the right agents.md or cloud.md, you can give the AI some clues about what the table structure could look like, so they can even ask questions without knowing what the data looks like. And often AI is integrated with other tools, so you can have it build all this stuff or do queries and then share it with other tools, and it makes it a really fast pipeline. So let's try a live demo. All right. So first I'm going to show superset. So I have just a bunch of mock data that basically is a fleet of about 10,000 Macs, where it's sending the OS version every hour. And I'm simulating enforcing various macOS versions as they're released and as they come out. So you can see on the left, this is like a live view of here's the current, status of the fleet. And you can think this is to the minute, right? So you get a live view. And then also useful is to see what does that look like over time. You can sort of see the pattern of each OS getting released. Superset also has a, just like a SQL playground, so you can run whatever query you want against the data. Next, this is the chat UI that uses the MCP I talked about. So I'm going to ask it to look at that same OS version data and just build me a bar chart distribution very similar to superset. And while that's going, I'm actually going to ask it another thing. So one of the nice things about osquery is, again, you can do custom extensions. So for this demo, I built a custom extension that queries the AWS Cost Explorer API to tell me how much this demo has cost me. So we'll come back to this one. So you can see it's running these tools, searching the table. It's getting the data. And again, this data is actually, it's not getting all the data because it's 5 million records. So instead it's querying it and writing it to a CSV. And it wrote a Python file, generated a chart, and then told me what the image was, and then the UI shows it, and you can see it looks very similar to the other one. And it, gives me some nice stats. So now maybe I want something more live, or I want to look at a specific date. So I'm asking it, to give it to me in the shape of a bagel. So we'll see how that works out. And it looks like so far I've spent $25 on this demo, so that's not too bad. So fun fact, it turns out the Cost Explorer API, every time you call it, it costs 1 cent. And I didn't realize that, and so I had it running overnight, sending that every minute, and it turns out that the highest cost I've had at this demo was actually just checking what the cost of the demo was. So it doesn't do that anymore. Let's see, this one's still going. Oh, there we go. I guess that's it's got some sprinkles, it's kind of a bagel. And lastly, I talked about metrics. Here's some metrics that we have from both the Flink job. So it looks like it ingested about 30,000 records a second. When I'm not on college campus Wi-Fi, it can do about 100,000 records a second. You can see here the specific records that came in from the custom extension, and then here's all the records from the simulated device. All right. So I know what you're saying, right? That's really cool. That sounds like a lot that I would have to build and maintain. And like I get it. I totally agree. It takes a lot of effort to build and maintain infra, and there's like what, like 6 components that I showed. If you don't have the capacity to build or maintain a data pipeline yourself, you do have the option of paying someone to do it for you. And the good news is like these are all fairly industry standard components that can be swapped out individually with commercial services. So this isn't an exhaustive list, but basically there's a equivalent in your favorite hyperscaler that you can implement this. Or, you can Google data lakehouse SaaS, and you'll find some companies that would love to sell you the full pipeline and the data access, every layer of it, all in one. Finally, if your company is large enough, it's probably already has a team managing data. If that's the case, there's likely already a data pipeline system that you can hook osquery into. And that also means that osquery data can be queried alongside company data like inventory and user and group information and authentication events. And this is where it becomes most powerful because you can start to answer questions beyond just your team scope. So, what should you take away from today? First, an osquery data pipeline can empower you to answer the important questions about your fleet. You can do it both right now and sometime in the past. And AI makes that data easy and fast to query. And finally, you have options. You can start small and easy. My goal with this talk isn't like to convince everybody to build this open source pipeline, but really just to show you what's possible, like what sort of things you can start thinking about when you have access to this data. And just hope that you explore, what options you have that will work for you. So that's it. Thank you. This QR code will take you to the GitHub repo for this talk, which contains like all the source code of everything I showed, as well as Terraform, where you can run the demo in like 15 minutes and it'll set everything up for you.